So first of all, thank you, Simon, for inviting me, for asking me to come and give a chat or give a talk about this work. I think it's really cool to see that there's this biosensor community growing and just people taking it from very different angles. So I'll introduce you a little bit to the work of one PhD student in our lab who's been working on these pyruvate biosensors using a transcription factor. And basically, we were looking at how can we engineer, how can we optimize this biosensor for for more reliable outputs. And so this project kind of came from a more bioprocess background. As Simon mentioned, I'm more of a bioprocess engineer in my background. And there, one of the key limitations we're always facing is that we get a lot of electronic information from sensors. Like you can have probes, pH probes, dissolved oxygen probes, things like that. And that's easy to get that information, but that doesn't always tell you so much about the biological information, right? What's actually happening with the metabolism of the organism and the microbes catalyzing the process that you're actually interested in. And that's where these whole cell biosensors have emerged in the last 5 to 10 years, let's say, where here it's represented as a target analyte coming from outside, but actually we could also be looking at target analytes that are produced or consumed inside the cell. We get some signal transduction, we get an output signal that we can actually measure even in the bioreactor. That would be an ideal case because then we can start probing what is the cell doing inside the system, right? So, as we were developing this idea, one target that came up was to look at pyruvate because it's so central in the carbon metabolism. It's the end product of glucolysis. Pyruvate itself can go to a range of products like lactic acid, alanine, via other pathways, also ethanol and butanol, but it also connects to the TCA cycle. So it's depending on what product you're making, depending on the process you're looking at. It's actually a combination of both. It could say something about the product you're making, but also about the anabolic state, so biomass synthesis of the organism. Or if you're having products that are derived from the TCA cycle, it's also really interesting still to measure pyruvate. One of the key issues with that remains that how to measure it in situ, so in your process. Current techniques are often HPLC or assay kits, but that's of course labor intensive and not really an online signal. Um, and if we're looking at biosensors, we want to have a system that we have a metabolite concentration. As metabolite concentration increases, we'll get different outputs. And there, a couple of key metrics become really important. So there's what's our basal expression, so what's our off state essentially. What's the dynamic range? So how big is the difference between that baseline and the maximal output? And then the sensitivity, so what's the slope of the curve within the working range of the system. And often we need to engineer this, right? So if we have a other way. If we have a first design of a biosensor, we'll get some curve, we'll get some response curve, but we actually want to optimize it so that I'm going too fast. We can actually want to optimize it so that we have lower basal expression, higher maximal expression, and a better slope and operational range. But that's easier said than done, and there it's good to have a rational approach to how we want to engineer this response curve. Here again, synthetic biology has really embraced this design, build, test, learn cycle. So in the design phase, we'll design a library, a range of pathways inside specific hosts that we pick. We'll assemble the parts, build everything that we need to, then test it using ideally high throughput screening or whatever approach we can get our hands on. In our case, we didn't go that far, but we still have the test cycle in the test part in there, of course. And maybe critically is that there's this learn stage that we use depending on who you talk to, but in our group, we really interpret this as you use mathematical or statistical models to interpret the data that you get from the test phase. Because using these models, you can get a more mechanistic or a more fundamental understanding of the system that can then immediately push through into a new design cycle. It's for us, we see that mathematical modeling is really a key component of the DBTL cycle to help accelerate that. And for this story, I'll get to the start of our design phase in a second. But basically what we have, okay, this jumped, but basically what we have is kind of a DBTL cycle. So we first designed a basic system, built and tested it. Um, and then once we had that system validated, then we had a full DBTL cycle that we completed, and now we're actually continuing to build on this and follow up research. But I'll focus on this one complete DBTL cycle for today and how and to what extent we could actually engineer this biosensor. So click a little bit. All right. So with that, I think we can actually get to the meat of our biosensor design. And most of what not most, but all of what I'll be presenting here is actually the work of Jihan Gao. She's a PhD in my group, um, who completely, yeah, for me, this is also kind of a new research line, but she very independently designed the system, started building it, really exploring it in a very nice way. So I really want to emphasize her work in this. And so to start with, we of course had to design the system where we have, my mouse is here. So we have this PDHR system. So we have a PDHR that's actually repressing the promotion of GFP in the absence of pyruvate. Once pyruvate is present, it binds to PDHR, it releases, and then GFP can be expressed in the cell. So it's quite a simple, straightforward system in that sense. That could be built quite easily. So this is then the design. One critical step here is that because we're using PDHR, we worked in a PDHR knockout strain just so that we weren't getting interference from the native expression of this repressing enzyme. And for the record, so in the genome itself, this PDHR is actually repressing the activity of pyruvate dehydrogenase. So this critical step again in the pyruvate metabolism. But because this is a pyruvate sensing molecule, we wanted to use this to control our biosensor. Jeff, Jehan constructed this quite simple system. So the constitutive expression of the PDHR, and then this was controlling the GFP expression in the other direction. Okay, time to test. So we just tested this biosensor at a range of pyruvate concentration. So this is just external addition of pyruvate. And you can already see if you're looking closely, 0, we don't get any GFP expression. 10, we're getting maximal GFP expression. So that looks like in the right direction. If we then look at the 6-hour mark, we can actually draw quite a nice line through our response curve. And basically we have a first kind of test baseline of the pyruvate biosensor. So we could operate this in a range of 0.05 to 10 millimolar. The lowest concentration where we got a significant signal was 0.05 millimolar of pyruvate, of external pyruvate addition. Okay, so like I said earlier, we have this baseline. Now we want to actually start engineering it, right? So this is, I showed this earlier too. So what are actually some of the opportunities? Sorry, and we want to, I was forgetting this part, but we want to get it to this optimized, so lower basal expression and better response. In this system, we decided to focus not so much on the pyruvate affinity of the PDHR, because in a sense, we also assume that the PDHR would have some affinity in biologically relevant ranges. But instead, we were more interested in playing with these the promoters and the ribosome binding sites in the sense of to what extent can we control the expression and the translation of these systems. Even in this system, the number of constructs that you have to make goes up quite quickly. So we had two promoters, two RBSs that we wanted to put at two levels, right? So strong promoter, weak promoter. If we would make all of the possible combinations, that's 16 constructs. Not impossible, but we can actually be a little bit smarter about this using design of experiments-based strategies. And there we can use what's called fractional factorial designs to have to only need 8 constructs to still identify, okay, which of these elements is still the most important. So it's basically a way to save some time in the test cycle or in the build and test parts of our DBTL cycle um, to help us identify, okay, which of these do we actually need to pay attention to, which of these can we kind of ignore. The downsides of this, of course, with less experiments, you get less information. What you lose is what's called factor interactions. For instance, if um, you get interactions between promoter 1 and promoter 2, you will not catch that. If a strong promoter 1 changes what the role is of promoter 2 in the system, it would be harder to catch that using this design of experiments-based approach. But for us, we consider that okay because we actually really wanted to focus just on the main effects in the system. Okay, so then comes testing and testing. So actually building and testing I should have put because Johan built these 1, 2, 3, 4, like these 8 strains. And the 0 is then the baseline that she built in the first cycle. I just copy pasted the same image here, but basically for all of these strains, she did the same analysis. And then comes actually the more tricky part is if you want to identify what these factors do in your system, you actually need to very carefully consider which metrics you want to optimize. And as I was mentioning earlier, this response curve has a couple of key features that we can look at, but each of these could actually be optimized almost independently. So we have an off state, we have an on state, and then we can look at the span, which is the difference between the absolute difference between on and off, and the dynamic range, which is the ratio between on and off. And so these are all quite commonly used metrics to quantify the performance and the usability essentially of a whole cell biosensor. So here on the right, you see all of the 9, at this point, 9 curves. Here at the top, we have the original strain, and we see, if I'm not, yeah, we have the original strain. And you see that a lot of these have lower basal expression. We have some that seem to have lower spans. But to identify, okay, which of these promoter and RBS elements actually contribute to the performance of this biosensor, we need to use a bit more statistical analysis behind it. And so that's what I'll be walking through in the next few slides. Because basically we can look for each of the metrics I mentioned. So we can have for each of, sorry, in this graph, you can see for each of the constructs, the off in blue and the on state in purple. And we see, yeah, you can see, for instance, massive variations in the off state. We see quite some variation in the on state. And basically, the off state we want as low as possible. From our statistical model, we can see that to get a low off state, we want a weak RBS2. So we want to minimize or we want to slow down the translation of the GFP itself at the end of the process. On the other hand, for a high on, you want a strong RBS2. So you already start seeing, okay, this makes sense mechanistically, but for some of our optimization efforts for the strain, they might be contradicting each other a little bit. For span, the difference between the off and the on states would really, the only factor that really contributed in a significant way is the RBS1, so the RBS for the PDHR. And then the factor that we'll continue to focus on most in the next couple of slides is the dynamic range, because this is really the ratio between on and off. So it's really the most commonly used approach to optimize these kind of biosensors. And there we saw that, again, a weak RBS2 is really the critical factor that contributes um, to a good biosensor performance or to a good dynamic range of the biosensor. Okay, so from this we get some information on the handles that we can tweak in the system. But we want to go a little bit further, and basically we also looked at can we predict the biosensor dynamic range based on this statistical model. So we didn't validate the model by building new constructs, but we did look at having like a full linear model, including this two-factor interaction. Once um, with the 9 constructs that we have, we look at what the experimental dynamic range was, what the model predicted, and those matched really well. The annoying part is that we have this 1-2 factor interaction that basically says there's a significant contribution from either the interaction between promoter 1 and RBS1 or between the interaction between promoter 2 and RBS2. But without additional experiments, we can't really identify which of these interactions matter. And basically that means that we don't know if we should keep promoter 1, RBS1 at the same level or promoter 2, RBS2 at the same level, or if it matters that one of the two is not the same. But we considered that, okay, for the sake of our application, this was actually sufficient. And we were more interested because here we actually got already a couple of key targets really improved in this whole cell biosensor compared to our initial baseline. We drastically reduced basal expression by having strain number 6 was the strain that according to the model would be the optimal strain in all ways, right? With the RBS in the right direction, or this weak RBS2 and also the other components according to this linear model. So we were lucky that it was already in our library of what we built. But this strain had much lower basal expression, because of that lower expression, had a higher dynamic range. But basically, I still mentioned them, but the span and the slope, yeah, more or less stay the same at the end of the day. It's a 4% increase, but that's not something that I would actually consider major improvements of the system. But at least for us, I think the dynamic range, due to that lower basal expression, was really what we were quite happy with. In all of these experiments, we added pyruvate externally to look at our biosensor response. And just to validate, okay, what's actually happening inside the cell. We also did some further experiments by looking at pyruvate addition and then measuring intracellular pyruvate. Of course, those units are not one-to-one comparable because we measure pyruvate intracellularly in micromole per gram of cell dry weight, whereas externally in millimole. But we could still see this quite nice response curve. I didn't plot the R squared, but it was also at the high end. I don't know it by heart, but it doesn't really matter. So, but we still got this very nice response curve that we could fit based on the intracellular pyruvate and the biosensor response. So we can show that this biosensor signal is really linked to the intracellular pyruvate concentration. So that's one, is that we have this validation of, okay, it's responsive to intracellular concentrations and not just to some kind of external signal beyond that. Okay, sorry, these graphs are a little lower quality than I anticipated. I'm sorry for that, but we also looked at how specific this biosensor is. So here we're comparing the response from pyruvate to the response from different growth substrates, so glucose, acetate, xylose. Basically, all of these give a biosensor or give a response from the biosensor, most likely because all of them actually end up yielding pyruvate inside the cell, right? So if you have acetate, we can move up back to pyruvate. If we have glucose, it's going to be converted. Glucose or xylose is also going to be converted into pyruvate. We also tested the specificity against keto acids to look more at the chemical level, because these are chemically, structurally similar to pyruvate. Um, and there we saw that oxaloacetate and alpha-ketoglutarate induced a response, which makes sense because our oxaloacetate is here, our alpha-ketoglutarate is here. These can be converted back up to pyruvate. On the other hand, glyoxylates and levulinic acids, these are chemically similar but did not induce any response in our system. So any of these other responses we really consider to be more transient due to metabolic processes rather than a lack of specificity from the biosensor or from the PDHR regulation itself. Okay, so I think then that was basically the main findings that we had. So in conclusion, we designed, implemented, and optimized this quite simple but still specific biosensor. We used this DBTL cycle approach to accelerate both the optimization and the mechanistic understanding of what are the key elements in the system that are regulating our biosensor response. And maybe one of the things I really learned from this is that we really always, because we want to like link learn to models, and we should already be considering how we'll approach the learn cycle during the design. So what models do we want to use? What metrics? And that's where this design of experiments-based approach can really be helpful because there you're using it already implies what the learn cycle is going to be even before you start building or even designing anything. It helps you accelerate the design stage, identify, okay, these are the key constructs I have to make, and really accelerates our interpretation and our understanding of the system. With that, I want to thank all of you for joining and for paying attention. As I said, this is the work of Jihan Gao, who did this. I also linked the QR code here for the preprint paper on bioRxiv, where you can read in much more detail everything that she did, everything that she built and analyzed. And with that, I want to thank you for your attention and open the floor to any questions from you.